Welcome back to Huawei Routing and Switching Elite Training for HCIE. Today topic we are going to discuss on IPv6. Let's start our part 3.
Right, so now we look into the enable discovery address resolution. Now if you still remember that IPv6 is a layer 3 protocol, okay, and they still need to connect to the switch or is a NIC card where they connect to a layer 2. So we need to have a layer 3 to layer 2 mapping. If you still remember in the IPv4, we use a protocol called address resolution protocol, and ARP basically is using a broadcast. Now this is where the problem comes. In the IPv6, we do not have any broadcast anymore. So how the address resolution is being performed for the mapping? Okay, so in the IPv6, the resolution are slightly different. In IPv6, we use a mechanism called neighbor solicitation, okay, or simply short form we call NS, and neighbor advertisement or NA. Now, as you can see from here, PC1 wants to get the layer 2 mapping on PC2. Now, what it does over here is PC1 is going to send an ICMP type 135. Now, when you send this ICMP v6, they also include the source of PC1 MAC address. And the destination is a solicited node multicast. So you can see that it's a multicast. So we know that multicast service start from FF0 something. Okay, and they also consist of link layer of a PC1. And this is a query. Now when this query reach to many of the PC which the PC1 requested will receive this query, or in this case a solicitation, and is going to reply through the advertisement, and this time the ICMP will be 136. So it will going to send the source, which is PC2. This is your data link layer, and it will send to PC1 in a unicast. Alright, so this is how the neighbor discovery address resolution is being performed. Now let's look into our Wireshark, alright, and the lab and see what really happened. Now here I have router 1 and router 2. Okay, so in router 1, let me show you. So this is the IP address I have, 2001.12::1. If I'm going to do a ping IPv6 to my neighbor 2001.12::2, I'm able to receive this information, but I still need to do the mapping. Now I do have a Wireshark already running. Let me check on the Wireshark. Now there you have it. You notice over here that we have the neighbor solicitation. You can see that this is FF02. Now FF02 has a significant value. The FF02 is actually an address resolution. Now if we look into the solicitation, you can see that the ICMP is 135. Now let's have a look. So if let's say we look into the solicitation, so this is a multicast, IPv6 multicast, okay, and this is the ICMP. So if you expand it, you'll notice that this is our 135. That's what I mentioned earlier on. So if we look into this is ICMP 135, and when we look into the reply, this is the reply. The reply is a neighbor advertisement, and you notice that this is in a unicast, and inside here it does consist of a layer 2 address inside there. So now you can see that how the resolution is being done. So we don't use broadcast, please remember that. So now the new mechanism is the neighbor solicitation and the neighbor advertisement. The rest over here is the ICMP v6. Alright, so next we look into what we call DAD. D-A-D stand for duplicate address detection. Now this is very similar to Gratitude's ARP in the IPv4. This is for you to detect any conflict of IP, and it's being implemented as an ICMP v6. And similar to the address resolution early on, they are using the NS and the NA. Okay, so when PC1 start to use the IP address, they are going to send out NS with a tentative address of 2000:1 as an ICMP 135. All right, as you can see that the source is : and they are going to send it through the multicast. The target address is 2001, so it will going to send a query: is any one of the PC is using this address. Now if let's say one of the hosts in the network do use a similar address, it's going to send a network advertisement mentioning that it is using this address, and PC1 will able to detect that there is a duplicate addresses. So let me show you what really happened in our lab. So if we just go back into router 1, all right, so I'm going to undo the IP address of the interface. Okay, so it's removed. All right, as you can see, it's removed. My Wi-Fi is still running. As you can see, that it's still in the blue color. So I'm going to do an IPv6 address 2001:12:2, which is IP address on router 2. Okay, IPv6 address with 64. Okay, so what will happen over here is you can see that it's actually go to the up, and we will just wait for a while. Okay, I let it capture this. Okay, and let me show you here. The address is not available. This is our link local. You notice that the address over here okay, it said that it's duplicate. You notice that? Now this is the mechanism on the DAD in action. So just to show you here, this is a neighbor solicitation. Okay, and this is the neighbor advertisement that I mentioned earlier on. And you can see that this is a 135, and this is where it's actually trying to say that, hey, I'm trying to use the 2001:12:2, and this guy also said that, hey, I am using that. So when the PC2, or in this case my router 2, detected it, it's actually sent a reply. All right, and this reply is in unicast. When it detected that there is a duplicate address, router 1 cannot use this IP. You can see that this is only a link local and not the global IP address. So you can see how the duplicate address detection is in action just now. So the mechanism is very similar to the address resolution, where we are using the neighbor solicitation and the neighbor advertisement. New to IPv6, we have a feature called SLAAC. SLAAC stand for Stateless Address Auto Configuration. Now the purpose of the stateless is to give a IP address or dynamic IP address to the host. Now this is being done through router discovery, and is being implemented using ICMP v3. So it discover router connect to the link local. So I have a router, let's call it R1, that connected to the same link to the host. So the host will obtain the prefix and configuration parameter for the auto configuration. Now the router is going to send a prefix, okay, and you also have to specify the prefix length, for example /64. Now together, when the routers advertise what we call the router advertisement, and the host send a RS, stand for router solicitation. Now the router is going to send a prefix together with the host, the link local, then it will get its IP address. Now it's being implemented using the ICMP v6 type 134 and you can see that the source is a link local of the router, and they are using a multicast. Now, inside the ICMP type 134 or RA, it contains the router lifetime, the current hop limit, the configuration flag, and etc. Now, over here, I'm going to show you one demonstration on how you can perform this. Alright, so let's go back to the ENSP. So here I have router 1. I've cleared up some configuration. So the previous configuration has been removed, and this is just the IPv6 enable. There's no IP address over here. Same go for the router 2 as well. Okay. Right, so you can see that there isn't have any IP address unassigned. Now I'm going to configure R1 as the Slack server, the stateless address auto configuration. That's our router, and R2 will be configured as a host. So firstly, the router must have an IP. So let's configure the IP address 2001:12:164. Now next we are going to configure to send the prefixes. Okay, so I'm going to use a command called IPv6 network discovery router advertisement prefix. The prefix I'm going to use is 2001:12:64, and the valid lifetime is from 0 to 4.2 billion second. Let's assume I'm going to use a 600 second, and preferred lifetime, let's say I'm going to say that is 600 again. Okay, is there any other? Alright, so we are going to do a enter, alright, to execute. That's it. So let me do a display this just to show you. This is a command for you to enable the router advertisement. And one more command over here is by default the network discovery router advertisement is not enabled, so you have to enable this. And for you to enable this, we have to use a command called undo IPv6 network discovery router advertisement hot. So we have to undo the hot. Right, so this is done. Let me show you the configuration. And now I'll go to R2. Now since R2 do not have any IP address, and we are going to configure the IP address through the Slack. So let me go to the interface. Okay, and just want to show you here there isn't have any IP address. Now we are going to use a command called auto. Alright, that is where we are going to use the stateless address auto configuration. Next, I'm going to look for the global. Okay, that's all. Enter. Now you can see that the interface is up. Okay, and when I do a display this IPv6 interface. Now what you can see from here, you can see that this is a Slack. Okay, there's a stateless auto configuration, address auto configuration, and you can see that this is the IP address that is given to me, and this is 2001:12. This is my prefix that I set on router 1. Now this is the MAC address that I have, 3F440. You can see that there's a FFFE that is using the EUI64. Okay, the format. Right, now if I'm going to check on my Wireshark, okay, now you can see that this is where my router advertisement, okay, and the neighbor solicitation. The neighbor solicitation is where we are actually configuring for the DAD, if you still remember. And here, this is where I have the router advertisement. This is my R1 to the R2. Okay, and this is the router solicitation. Okay, you can see that there's from here. And if you look into the content here, there you have it. Alright, so this is the type of 133. Okay, that's your solicitation, and you have the router advertisement that is 134. And as you can see from here, the prefix that we actually send is 2001:12::. Now if I'm going to go back here and I do a display IPv6 interface brief, as you can see that this is the IP address I have through the Slack. Okay, and I'm going to do a ping IPv6 2001:12:1, which is R1, and you can see that it's working. Alright, so this is where the new features on IPv6, we call it as a slack or the auto configuration. Alright, this is a stateless rather than stateful. Stateful is where we have the HTTP v6. Now let's look into the neighbor discovery redirection. Okay, so this is very similar to the IPv4 redirection. So this is the scenario. A gateway router sends a redirection message to notify sender of a better forwarding path. Now let's look into this topology. Now R1 and R2, alright, both of these routers belong to the same subnet with PC1. Now PC1 wants to go to PC2, but PC1 point to R1 as a default gateway. Okay, so naturally, when PC1 want to go to PC2, you're going to send the message to R1, then R1 is going to send to R2, and then from R2 send to PC2. Now this is not really efficient. Now one of the way for us to solve this is using the redirection. Okay, so after R1 receive a message from PC1, R1 is going to send a message, alright, to PC1 informing that, hey, this is a redirect packet with the ICMP number 137 with the source of router A, in this case this is R1, and the destination of PC1. The target in this case is router 2, which is in this case B, and the destination address is PC2. Alright, so inside the header, remember that in IPv6 we have a next header. There is one called redirect packet. Now subsequently, when PC1 want to go to PC2, it's going to send to router 2 instead of router 1. Now another new features on IPv6 is called path MTU. Now the path MTU protocol is implemented through the ICMP v6 packet 2-bit messages. Now let's look into this scenario. I have here PC1 and PC2 that need to cross 4 segments. Alright, so these are the 4 segments that need to be crossed. And you notice that the segment of PC1 and R1, 1005 and 1005, that should be no problem. But segment on R2, R3 and R3 to PC2, you can see that the segment size over here, or MTU here, is 1004 and 1003. Now it's very important for us to have a good MTU size to prevent the fragmentation, to reduce the overhead. Now this is how the path MTU in IPv6 work. Now firstly, the source is going to try to use the default MTU, which is 1500 byte. Now once you cross to R2 to R3, which is not 1500, now the ICMP is going to send an ICMP error packet 2 bit, and it's going to advise the source to try to use 1004 instead of 1005. Now with this new information, the PC1 from here is going to use a new information, which is 1004 going to R3. Now again, when R3 go into PC2, this segment is in 1003. Again, you have an ICMP error packet 2 bit. And now PC1 will try again using a new value of 1003. Now subsequently the path MTU is known. Now this is one of the features on IPv6 path MTU. Now over here I have a new topology. Here I have router 1, router 2. Router 1 connect to the host through a switch, and the host is using the dynamic IP. But what more important here is that R1, R2, this is a new segment, and as you can see that this is a gig 001. And when I go into the R1, I can show you that we have 2 IP address over here. So we have 2001-12 and 2001-112. So 112 is between 1 and 2. And I can do a ping IPv6 2001:112:2. That's on the R2. Okay, so you can see that it's working. Now for us to test on the path MTU, now this is what we're going to do. On R1, I'm going to reduce the MTU size to smaller. So let me go into the gate 001, and I'm going to do an IPv6 MTU. The size of the minimum MTU is 1280 to 1500. Now assume I'm going to do a 1003. Right. Now the default MTU is 1005. So on the host, alright, I'm going to try to ping to router 2. Now before I do that, I need to configure a default route. So let me show you how to configure the default route. IPv6 route static. So that will be my default route with a prefix of 0. I'm going to send to 2001:12::1. That will be the next hop of R1, gate 000. Okay, and press enter. Now next I'm going to enable my Wireshark just to show you that what will happen if, let's say, I'm going to do a ping, okay, with a big size. So I'm going to do a ping IPv6. I'm going to specify the size. Alright, so remember this is 1005 and here we have 1003. So I should use anything more than 1005. Let me try to use 1006. And I'm going to ping to 2001:112:2. Alright, so you can see that the first one here I have a timeout. Why? Because this is where the packet too big coming back to me with an error. Now let's just look into the ICMP. Alright, so let me do an ICMP v6. Okay. Right. So you can see over here that I have the packet here, and you can see that I have the ping request. That is the error. That is to say that it is too big. You see that? That is the type 2. And what really happened over here is that it's get fragmented with a data of 1248. And you can see that the subsequent one here, 128, okay, this is our ping. Then we have 1248. So it's actually get fragmented. Alright, so you can see that the size is actually 1310. So with this information, the path MTU, what it does here is that the ICMP help us to determine the end-to-end path MTU. So here you have the ICMP v6 with the path MTU in action.
Thanks for watching. Please do not forget to subscribe to our channel.